Hello, thank you for joining me today as we begin our discussion on the types of nuclear decay. And so last time we talked about the kind of introduction, just the basics behind nuclear chemistry and nuclear radioactive isotopes and when they break down and that kind of thing. So we're going to talk about the 5 specific types of nuclear decay we're going to discuss and use in this class. So we can get the types of nuclear decay. So at the end of this video, you'll be able to write the nuclide notation for alpha, beta, and gamma decay, along with positron emission and electron capture. And so if we show you the nuclide notation, so you'll be able to notice or recognize these symbols for these types of decay. And then given an equation or a reaction, a nuclear reaction, you can determine what type of decay is happening because you'll notice this particle. So that's what we're going to work through today. So let's get started right away with alpha. So if we're talking alpha decay, we're talking about an alpha particle, which is symbolized by this symbol. Looks like a fish. We used to draw those fish when we were younger. That's an alpha symbol. This is equal to a helium nucleus. So your alpha nuclide notation looks like this. They can either write an alpha particle like so, or they'll put 4/2 He. And this is what you'll see most of the time. But here you have your basic alpha reaction, alpha decay. So you have A over Z with X, and you have a particle here, and you have a helium nucleus. This is your alpha decay. Now, everything we do with nuclear decay is going to involve the mass number and the atomic number. These numbers are really important. So on this worksheet, the arrows is an equal sign. And then on this side, it's obviously a plus sign, means you're going to add them together. So you're adding everything on top and you're adding everything on bottom. They need to be equal. So for example, if I'll rewrite this first equation. And I'm just going to use an equal sign instead of an arrow. But I don't know my y. Plus, and then my alpha decay means I have 4/2 He. And I know that this is a mass of 4, atomic number is 2, and that's why this is helium. And so we can put letters here. I can just put question marks here is fine. Put X's there, that's all okay. So in this case, I know that A equals my question mark plus 4. I know that Z equals the question mark, I should put an X, plus 2. Okay, so now if I add numbers to it, so we've done all this. So now I'm going to tell you that radium-226 is going to undergo alpha decay. So I have 226 over 88, and I have radium is going to undergo alpha decay. So I know that I have X, because I don't know what that is, and I'm just going to put a little Y up here. I'm going to use a Y, and I'm going to use a, I should use an A, and I should use a Z. We'll use A here, and we'll use Z here. Plus, helium is 4/2 He. So now I know that 226 is equal to, the arrow means equal to, A plus 4. I can then subtract 4 on both sides, and I know that A equals 222. 226 minus 4 is 222. I do the same thing with the bottom. I know that 88 equals Z plus 2. So I'm going to subtract 2 on both sides, and I know that Z equals 86. So now I know my mass is 222, my atomic number is 86, so I can write those in. 222 over 86, I look at the periodic table, that's radon. This is the reaction, this is the equation for the alpha decay of radium-226. It produces radon-222. And this is what we're doing with alpha. And you'll get a chance to practice on the next video. Beta decay. A beta particle is an electron that comes from the nucleus. And so to understand beta decay, we need to talk first about quarks. So each a proton and a neutron are made up of these little smaller subatomic particles called quarks. There are two kinds of quarks. They call it an upspin quark and a downspin quark. For this, up equals positive, down equals negative. To make this course, for this course, we can look at it in that sense. So protons, I guess, and my upspin quark, which is positive quark, equals a positive 2/3 charge. My downspin quark, which is negative, equals a negative 1/3 of a charge. Okay, so protons have two upspin quarks. I'm going to put two positive quarks and one negative quark. And so protons have 2/3 of a charge for one upspin, plus 2/3 of a charge for two upspins, minus 1/3 of a charge for the downspin. So 2/3 plus 2/3 is 4/3, minus 1/3 is 3/3, which equals 1. That's where the charge of 1 comes from for a proton. A neutron has one upspin quark and two downspin quarks. So on this one, if I do 2/3 minus 1/3 minus 1/3, 2 minus 1 is 0 over 3, which equals 0. So that's how your neutron has no charge. Okay? So a beta particle is the loss of an electron from the nucleus. We don't have electrons in the nucleus, but we have these quarks. And so what happens in beta decay is you have a neutron that has a positive quark and two negative quarks. There's other free-floating positive quarks out and about in the world, just free-floating. And when they interact with the nucleus, this positive quark is going to come in, it's going to kick out a negative, one of these two negatives. So this one's going to leave. This is my high-speed beta particle leaving the nucleus. So in beta decay, and now this becomes here. So I went from a neutron to a proton. So in beta decay, your atomic number increases by 1. But my mass stays the same. Because protons and neutrons have the same mass, the mass number is going to stay the same. So here's how it looks. I have bismuth 210 undergoes beta decay, so I know I'm going to lose a beta particle. Okay, so I have 210 equals, I know beta doesn't have any mass, it's just got an atomic number of -1. This is my beta particle. You can write it as E, 0 over -1, or you can use the beta sign. Either way works. So this equals A plus 0, which means that A equals 210 for my leftover nuclide. On the bottom, I have 83 equals Z minus 1. So I'm going to add 1 to the other side. I know that Z equals 84. So bismuth 210 undergoes beta decay and becomes polonium 210. And that's shown here. Again, you're going to get a chance to practice this on the next slide, but I just want to get you the basics, kind of give you a little bit of a practice, and then we'll give you a chance to work through some on your own. So that's alpha and beta. Gamma radiation. Gamma decay is a high energy photon. Basically, gamma decay releases light. This is the symbol for gamma. It looks like a Y. This is how I draw my gamma symbols. But gamma has no mass and it doesn't change the atomic number. The way you'll see this a lot of times is you'll see something like this. So you have A with an asterisk produces A plus gamma. Okay, this little asterisk just means that it's got a ton of energy. It's a nucleus with a whole bunch of energy. And so it's unstable because of all this added energy. When it becomes stable, that energy is released as a gamma particle. So this is how you write gamma radiation. We have two more types that we're going to talk about in this class. One of them is positron emission. So positron is essentially the opposite of beta decay. So a beta particle is beta with 0, -1. A positron is the exact same thing, only the -1 becomes a +1. You can write it as, here's a beta particle, here's a positron, or you can write it like this. Either way works. A positron has a +1 for your atomic number down on the bottom. Okay? And so in looking at positron emission, if we have thorium-232 is going to undergo positron emission. So I know that 232 equals positron, again, no mass, equals 0 plus, and I'm going to have A over here. So I know that my mass is still 232. And then 90 equals +1, because it's a positron, not a beta particle. +1 plus Z. So I have to subtract that, so I know that Z equals 89. These become my two numbers. I look at my periodic table. There is my nuclide notation. So you have AC-232 for your actinium-232 for your product there is going to be your result. That's positron emission. And the last one is going to be electron capture. This is the exact same thing as beta decay, except the beta particle is on the other side. So this is still capturing an electron. So in this case, we're going to have a proton we're going to capture an electron. So that means that this negative is going to come into here and make this proton become a neutron. So that's how this is all going to work. So again, we're bringing in this electron. So we're looking at electron capture. I know that I have potassium 40. I know that 40, so we're looking just at the numbers, plus 0, there's my equal sign, equals my A on top. And so A equals 40. Mass doesn't change. On the bottom, 19 minus 1 equals Z. And so Z equals 18, because 19 minus 1 is 18. Look at your periodic table. 18 is argon. Potassium 40 undergoing electron capture is going to produce argon 40. This is electron capture. Again, I'm going to give you some practice questions on the next video, but this is your basics for each of the 5 types of radioactive decay. Here are some questions for you to just kind of give you a chance to look things over and think things through, and then we'll continue on tomorrow. If you have questions, please don't hesitate to ask. It just takes a little bit of practice, and I can maybe explain it a little better in person. But I hope that this helped you out, and if you have questions, please come see me when you return to school.